So welcome to the new video on our damage mechanism series. In this video we are going to talk about a damage mechanism known as cooling water corrosion. Now this kind of corrosion is very similar to microbiology induced corrosion because this will generally happen in water areas or wherever the water has been handled. This kind of damage mechanism is generally going to be very common in heat exchanger tubings, and in some cases it can also be present in pressure vessels. This is not common in piping systems, but again, if your piping is handling water, then this is possible. So the description of the damage, this kind of damage mechanism is much more suited towards pressure vessel or API 510 examination, but again a damage mechanism nonetheless. So description of the damage: general or localized corrosion of carbon steels and other metals caused by dissolved salts, gases, organic compounds or microbiological activity in cooling water systems. Affected material: carbon steel, all grades of stainless steel, copper alloys, aluminium alloys, titanium and nickel alloys. Critical factors: cooling water corrosion, fouling, microbiology induced corrosion are closely related and should be considered together. Fluid temperature, type of water and the type of cooling system, oxygen content and fluid velocities are critical factors. Higher cooling water temperature increases the corrosion rates. Always remember one thing: whenever the temperature increases, generally the corrosion increases. This has some exceptions to it. So when you talk about corrosion under insulation, at a temperature above a certain temperature, you will generally not find corrosion under insulation. But generally, in general cases, as the temperature increases or as the pH value of the electrolyte increases, you will have generally accelerated corrosion rates. If you have higher velocity, you will have accelerated corrosion rates. So higher cooling water temperature increases corrosion rate. Increasing cooling water heat exchanger outlet temperature and or process side inlet temperature tend to increase exchanger bundle corrosion rates as well as fouling tendencies. If the process side temperature is above 140 degrees Fahrenheit or 60 degrees Celsius, a scaling potential exists with fresh water and becomes more likely as the process temperature increases as the cooling water inlet temperature rises. Increasing oxygen content leads to an increase in carbon steel corrosion rates. Fouling may be caused by mineral deposits, slits, suspended organic materials, corrosion products, mill scale, marine and biological growth. Low velocity can promote increased corrosions. Velocity should be high enough to minimize fouling and drop out of the deposits, but not as high as causing erosion. Velocity limits depend on the pipe diameter or heat exchanger tube material and water quality. Oversized channel heads, water side exchanger shells or dead legs can be area of low or stagnant flows. Generally the velocities of below 1 meters per second or 3 feet per second are likely to result in fouling, sedimentation and increased corrosion in freshwater and brackish water system. Accelerated corrosion can also result from the dead spots or stagnant areas if the cooling water is used on the shell side of the condenser coolers rather than preferred tube side. High velocity can also lead to accelerated corrosion. Exchanger tubes can see a dramatic increase in the flow velocity. 300 series SS, depending on the specific alloy and the temperature and the metal temperatures, water and metal temperatures, can suffer pitting and crevice corrosion. The temperature above 60 degrees Celsius or 140 degrees Fahrenheit, 300 series SS can also suffer chloride stress corrosion cracking, even in the freshwater systems where chloride salt containing mechanism is in place. This is particularly concerns with the tube in the water cooled heat exchangers, that is condensers and coolers. Brass alloys can suffer dezincification in fresh brackish water and saltwater systems. They can also suffer stress corrosion cracking if any ammonia or ammonium compounds are present in the water, or on a process side if the cross leakage occurs. ERW carbon steel pipe or exchanger tubes may suffer severe weld or heat affected zone corrosion in fresh or brackish water. When connected to more anodic material, the titanium may suffer severe hydriding embrittlement. Generally the problem occurs at the temperature above 75 degrees Celsius or 165 degrees Fahrenheit. Affected equipment: cooling water corrosion is a concern in cooling towers, piping, pump, water cooled heat exchangers and any other equipment associated with cooling water systems. Appearance and morphology: So cooling water corrosion can result in many different types of damage, including general corrosion, pitting corrosion, microbiology-induced corrosion, stress corrosion, cracking, and fouling. General or uniform corrosion of carbon steel occurs when the dissolved oxygen is present. Many oxidizing biocides also increases this tendency. Localized corrosion may result from under-deposit corrosion, crevice corrosion, or MIC. Wavy or smooth corrosion at the nozzle inlets or outlets and exchanger tube inlets may be due to flow accelerated corrosion, erosion, or abrasion. Corrosion at ERW weld areas will appear as grooving along the weld fusion line. Prevention mechanism. Cooling water corrosion is best managed by proper design, operation, chemical treatment of the cooling water systems. Process side inlet temperatures of water cooled exchangers should be maintained below 140 degrees Fahrenheit or 60 degrees Celsius. Okay. So generally, as you increase the temperature, the corrosion is going to be generally higher enough. So generally, we'll try to keep the temperature low enough so that this will be minimized. Inspection and monitoring. The cooling water should be monitored for the process conditions that affect corrosion, fouling, but not limited to pH level, oxygen content, cycles of concentration, biocide and other chemical residue, biological activity, iron and manganese count, cooling water outlet temperature, hydrocarbon contamination, process leaks. Periodic calculation of the overall heat exchanger performance will provide the information on potential scaling and fouling. Now again, if the problem is the exchanger tubes are best inspected with eddy current inspection, especially with remote field testing, but sometimes eddy current inspection can also be done. So exchanger tube inspection can be used to establish corrosion rates and predict life of the tube in order to plan for the tube or tube bundle repair or replacement. Some non-destructive methods used to inspect tubes are as follows. RFT is commonly used for inspection of ferrous tubes. RFT is an equal sensitivity to ID and OD indications and can detect and size the corrosion and pitting as well as baffle cuts. Eddy current testing is preferred method for non-ferromagnetic materials as it has higher probability of detecting all types of damage than ultrasonic methods. Ultrasonic method has a limitation that it cannot check the materials that are below 5 to 6 mm. So if it's a very thin material, then ultrasonic testing would not be a preferred testing method. Internal rotary inspection system is used when higher flaw detection and sizing capability is needed, but it is slower and thorough tube cleaning is required prior to the inspection. Iris can be used in both ferrous and non-ferrous materials. Iris is most commonly used on carbon steel tubes. There are some relative mechanisms associated with this, so we have all seen this. We have seen microbiology induced corrosion, we have seen chloride stress corrosion cracking in this series. We have also seen galvanic corrosion, concentrated cell corrosion. We have not seen brine corrosion, but that is also associated with this kind of damage. So this is what it looks like. Now in this case, you can see that it is looking like most of the other common mechanisms. You can see this as corrosion erosion. You can see this as microbiology induced corrosion. You can also see this as chloride stress corrosion cracking. So all of these damage mechanisms are to be understood in a group, and accordingly remedial action can be taken. Okay. Common damage mechanism for cooling water corrosion. In the next video, we'll be talking about some other damage mechanism for our damage mechanism series. Thank you.